Okay, so today we're going to talk about rotational spectroscopy. We did vibrational spectroscopy last time. We talked about all the different fundamentals that we see. It is again? Why? I wonder what happened. When I killed that PowerPoint, it blinked and did something strange. Laptop not detected. This is set to mirror. Okay. Come on, please work. Yeah, okay. So we talked about the vibrational spectroscopy last time. And in the infrared spectrum that we get in lab, what we're really looking at is all of the fundamentals. And we went through 2 lectures ago all of the acetonitrile vibrations, the deformations of the methyl rings or methyl groups and the CN stretch and the CC stretch. And so whenever you're looking at an infrared spectrum, just think these are all fundamentals. Now, there are a few peaks that may be combination bands or overtones, and we'll talk about those not next time, but on Monday. Okay, so we'll go through all of where the combination bands come into this and so on. But in general, those are all fundamental vibrations. And the peaks are just single peaks in the liquid or solid phase. When you get to the gas phase, then you start to see other things happening. And one of those things is rotation of molecules. So molecules can freely rotate in the gas phase, and they can absorb light. So before we get into row vibrational spectroscopy, where we have rotation and vibration added together, let's just talk about rotation by itself. So that's what we're dealing with here. This is rotational spectroscopy by itself. And we're going to be dealing with the rotational energy levels. Now, let's think about this. We have this, you know how in the particle in a box, we have that constant that comes out front whenever we do a transition equation. And that constant has like h squared in it, and in the denominator has the mass, and it has the length of the box. We're going to see this kind of behavior in all of these different energy equations. And the one that's most closely related to what we did with the particle in a box is rotational motion, because it's really like a one-dimensional system. So you're rotating around a particular axis, and so you have a rotation angle. So you could take that idea of the particle in a box, you could put it into a circular box and call it a particle on a ring and solve for it, and you get a very similar equation to what we got. Doesn't that look familiar? H over the pi is new, but you have the speed of light in the denominator, and you have this thing I called the moment of inertia. But if you look at that moment of inertia, it's the mass times the radius of rotation, which is like a box length squared. So the radius is squared. That's very much like L squared. So that's why I think this is valuable to go through that whole long thing of particle in a box, because it tells you about these real systems, and you have an intuition that the size of the system's in the denominator, and the mass of the system's in the denominator. So if I increase the mass or increase the size of the system, my energy levels are going to get closer and closer together. And it's going to be more difficult to resolve them in the spectrum. Now, the moment of inertia is the distance, not like the bond length here. This R in the moment of inertia is not this bond length, right? That's not R. I'll put an X across R there. Okay, it's the distance from the axis of rotation. So that's that mass times that distance from the axis of rotation squared. And then you just add all of those up. So the moment of inertia is the sum of all of those masses times the distances from the axis squared. And that gives you that thing that's sort of acting like a mass in the denominator. It's moment of inertia. And so you have, like if you're rotating water, the hydrogens, if we're rotating around that C2 axis, this is the distance that we're talking about here, not the bond length. But they're related to each other. You know, you could do a tangent of the angle, and you could get the ratio of the RH over the RZ and get the hypotenuse and so on. So you could solve for these things with a little bit of geometry. And we do that in terms of finding molecular structures. So rotational spectroscopy is one of the best tools we have for solving for the structures of molecules. And that's what you're going to do for the carbon monoxide lab. You're going to look at row vibrational spectroscopy to solve for the bond length. Now, diatomic is super easy because it's just one dimension. It's just one bond length. Now, one thing you have to have, though, for it to interact with light, if you're just doing pure rotational spectroscopy, is you have to have a rotating dipole, because light's coming in with an oscillating electric field, and unless that, this is a good example. This is, it's got, if we're treating this, so this cap as a negative charge and this end is a positive charge, and you've got an electric field coming in, oscillating at a certain frequency. If it's rotating at around that same frequency, it can absorb that light. It can receive a kick, and it can go up to a faster speed of rotation. And if it rotates faster, where'd that energy come from? It came from the absorbed photon of light. So let's look in terms of what magnitudes of energies we're dealing with. So I call this the energy landscape, right? If you're new to an area and you're up on the hill, you want to see where are the mountains, where are the valleys. Let's look at the landscape here. So we've talked about electronic spectroscopy. Our particle in a box was in the visible region, and so we were dealing with energy levels that were very far apart. Okay, kilojoules per mole, far apart. And if you were to zoom in down there at the ground state, you would see the vibrational levels. So the vibrational levels are not in the visible region, they're in the infrared region. And that means that those energy levels are really close together. Okay. We're not in the sort of what we consider light, we're down in the heat region. Okay, infrared, lower than red. Okay, lower energy than red, longer wavelengths. But if you were to zoom in on the ground state of each of the vibrational motions, then you would see the rotational levels. Okay, and that's in the microwave region. And so your microwave oven it's not a spectrometer, because the meter part, it's not measuring anything, it's not a meter, but you could do microwave spectroscopy with all of the pieces in that microwave. Okay, we just need to add a detector. Okay, we have the source. And why do we use a microwave oven to heat our food? Well, think about it. This is rotational motion, and water has a permanent dipole. And so if you were to put a microwave source and aim it at food that contains water, you could oscillate or try to oscillate that water molecule. Even if it's in a solid or liquid, it's going to try to spin. And you're going to try to spin that water molecule, and it's going to absorb that microwave energy, and it's going to bang into the food molecules that are around it, and it's going to heat everything up. So light is opaque to that microwave generator, and it just absorbs all of that energy. So it's really the water in your food and anything else that might absorb that same frequency that's heating your food. And that's why if you overheat something in the microwave, you really turn it into like a rock, or try it with bread. If you overheat a biscuit, it's like a rubber biscuit after a while, because you've driven all the moisture out of it, and it's just inedible. Okay, so my pro tip, especially for like a hamburger patty or something, you don't want that thing to get too hard, because you still want a nice juicy hamburger patty. So you put that on a plate, and you put a dry plastic, because plastic is transparent to these microwaves, over the top of it. And so the steam, the hot water that leaves the patty, is captured by that plastic cover and drives back down into the meat patty. And so that gaseous water is really going to absorb a lot of microwaves, and it's going to have a lot of energy, and it's going to go back into that hot hamburger patty. So give it a try. It's really good. So the microwave is really tuned to water. That's the point of all of this. And microwave wavelengths are really long compared to infrared wavelengths. And those are long compared to visible wavelengths. So we're way down in low energy areas, just causing the rotations of molecules. They have to have a permanent dipole moment, though, to absorb that light. So that's why this is circled in red. So for rotating molecules to absorb light directly, they have to possess a dipole moment. And all polar molecules possess that permanent dipole moment. Not polar bonds, permanent polar molecules. So you can have like carbon tetrachloride. So carbon surrounded by 4 chlorines. Each one of those bonds is polar, but the molecule itself is nonpolar. Okay, does that make sense? Because all of those bonds are aimed in towards the carbon. I can draw that real quick. So you have carbon here, chlorine, 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 and chlorine. So there's carbon tetrachloride. Each one of those individual bonds is polar, but the whole molecule is nonpolar because all of those little dipoles cancel each other out because it's a symmetric molecule. And so this molecule would not have a pure rotation spectrum. Same with diatomics that are homonuclear, so O2, N2, and this is key to our survival because the sun is blasting us with like 1.5, let's see, what is it? It's like 1.5 million exajoules per year. It's an incredible amount. It's thousands of times more energy than we use in a year globally. The sun is just blasting us with this energy, but it's in the visible region primarily, and whatever does make it through our atmosphere then needs to exit. And if the atmosphere absorbed the infrared light, then the greenhouse effect would run away from us. So the greenhouse effect is what keeps us from freezing to death at night. And it's mostly water in our atmosphere. CO2 plays a role, but water is the main greenhouse gas that makes the planet inhabitable. And so water absorbs some of that, keeps us warm. But if CO2, well, we'll stick with nitrogen and oxygen. If nitrogen and oxygen directly absorbed infrared light, none of that heat could escape the surface of the Earth and make it back out to space. It goes right through the nitrogen, right through the oxygen. But you start adding a third atom there, then you start to have motions, vibrational motions that can absorb light. So rho vibrational motion can absorb this infrared light. Now the selection rules are plus or minus 1. So delta J is plus or minus 1. Now in our particle in a box, it was 1, 3, 5, 7, 9, all of the odd ones. But for rotation, it's just plus or minus 1. And one of the reasons why is because light has 1 unit of angular momentum. Okay, so it can give light a kick. If it's already rotating and light comes in, it's rotating in the same direction, it can give it a kick at higher angular momentum, or if light's operating in the opposite direction, it can slow it down a little bit. So that angular momentum of light can be added to the angular momentum of the spinning molecule, or it can be subtracted from that. Raman transitions involve 2 photons. So what do you think delta J is for that? I know you have it in your notes, but think about it. Okay, plus or minus 2 or 0. So those photons, if you think of light coming in, just a photon of light, it has an electric field that's oscillating, and 90 degrees a magnetic field that's 90 degrees also out of phase. And so it's up, then magnetic, then it's negative in terms of electric field, and then it's like south, I guess, for magnetic poles. We call them north and south, and then positive, north, negative, south. And so do you see the rotation? So it's like it's rotating this way, or it could be going in the opposite direction. It could be positive, north, negative, south. And so it could have an opposite sense of angular momentum, but they have 1 unit of angular momentum each. And that can be added or subtracted from the molecule's rotation. You add in 2 photons, they could all be together, they could be opposite each other, and they could be opposite relative to the molecule. So you could have plus or minus 2 or 0 for Raman spectroscopy. Now, I didn't like that. I liked symmetry. We can explain the particle in a box selection rules with symmetry. We can explain vibrational rules with symmetry. We can see the wave functions and so on. And I didn't like this in my PChem days, that we get to rotational motion and all of a sudden angular momentum comes out of the blue. We haven't talked about angular momentum at all until now. When we get to rotational motion, we start talking about angular momentum for the selection rules. And I just thought it felt what they call ad hoc. It's like, for this case, we're going to pull in an angular momentum argument, but we're going to use symmetry for all the others. And so I asked my student who was doing research for me if they would like to work on a paper where we could figure out the selection rules for rotational motion using symmetry, not angular momentum. And we didn't know if it'd work. I mean, I kind of thought it would, because symmetry of the wave functions, pretty much governs all of these behaviors. And sure enough, it worked. So we published this paper in CHEM Ed, and and then she wrote her thesis on it. So that was cool. That's Victoria Jackson, and then she graduated. Yay. Okay. So now we have a description of the rotational selection rules using symmetry. It's just a different description of the same phenomena. I mean, you can use angular momentum arguments. That's great. It just seemed like we were pulling that out of the blue at this part of the course instead of sticking with symmetry. And so we determined that symmetry can also explain it. So we're dealing with pure rotational absorption. And so in those transition equations, those transition frequencies, they're separated by 2 times that rotational constant. And so I've indicated here the difference. As you know, I'm always pointing out the difference between lines and levels. So up here, here's the energy level diagram. And every transition is a difference between those levels. So these little red lines really should be arrows. Okay? But it's just a lot of tiny little lines. And so in that energy level diagram, you're very familiar with this now. This far into the course, you have 2 levels. You draw an arrow between them. That's a transition. And that's going to give you a spectral line. So below all of these, you have the different spectral lines. And so this is the data that you get. Right? If you go in and you have a microwave source and you have a detector and so on, you would see these different rotational lines. And they have an interesting intensity. This, as energy goes up, okay, so this population of the energy levels goes up because G of J is equal to 2J plus 1. So that's the degeneracy. And as you go up in rotational number, or rotational quantum number, you have more energy levels that are degenerate. And so because you have more chairs, you've got more molecules in those chairs. I kind of think of it as musical chairs. We're gonna let nature come to equilibrium. We're gonna take a measurement and see where all the molecules are sitting. So this increase in intensity is because of the degeneracy. But eventually you start getting such high energy that the Boltzmann factor starts to kick in. And so this drops down because of the E to the minus EJ over KT. And so that profile that you have for the rotational spectrum is both that degeneracy factor and the Boltzmann factor multiplied by each other. And you get this rise in intensity and this drop off in intensity. The cool thing is it's temperature dependent. And so we can use this envelope of rotational lines to measure the temperature of the gas. And so we have satellites up there that are looking at the sun through the atmosphere and getting a rotational spectrum or measurement of our atmosphere, and they can measure the temperature of our atmosphere using the Boltzmann distribution. It's pretty cool. Okay. So this spectrum also gives many measurements of B, because every one of those lines is spaced by 2 times the rotational constant, 2B. So since we have lots of measurements of B, we have a good average and standard deviation, and this gives us good bond lengths and angles. But there's a maximum of 3 rotational constants. If it's an asymmetric molecule, you have a rotation around X, rotation around Y, rotation around Z, and that'll give you 3 equations. But if you have more than 3 bond lengths and angles, you have way too many unknowns. And so we can use symmetry. It says, does symmetry help? Yes, because look at water. We have 2 bond lengths and an angle, but those bond lengths should be equal. So we really only have 2 parameters in water. We have the angle and then the bond length. And the bond length is the same because the atoms that are connected are the same. But for ethane, we've got 7 bond lengths and 1, 2, 3, 4, 5, 6, 7, around 8 angles for that molecule. And so we've got a lot of unknowns. But we could use symmetry. We could say all those CH bonds are the same. So we really have a CH bond length, a carbon-carbon bond length, And the methyl group should be symmetric, okay? So we really just have that sort of umbrella. How wide is the methyl group? So that's an angle that would tell us how wide or how opened up that methyl umbrella is. And so that's an independent angle. And so really, we could reduce with symmetry methane's structure to only 3 parameters: the carbon-carbon bond length, carbon-hydrogen bond length, and then that methyl umbrella angle. And once you have those, then you can solve for all the others. So in ethane, we could get the structure of ethane using rotational levels. We have 3 unknowns, we have 3 rotational constants. If we could get a spectrum of those, we could solve for the structure of ethane, even though it's got 8 atoms. We would have to use Raman spectroscopy on that. Why? Is ethane going to absorb microwave light directly in its rotational energy levels? It does not have a permanent dipole moment, right? So you just constantly remember, if you have to do direct absorption in rotational spectra only, so pure rotational spectra, you have to have a dipole moment. So ethane wouldn't absorb light directly, but you could get a measurement in Raman spectroscopy. Since it's a 2-photon process, then you have different selection rules, and you can interact with molecules that don't have a permanent dipole moment. So here's the spectrum for pure rotational Raman. You have the energy level diagram at the top, and the pure rotational spectrum, the spectral lines down at the bottom. So basically, any molecule that has electrons, which is all of them, will interact with light using its polarizability, so the flexibility of the electron cloud. No dipole is needed, and these are the selection rules. So let's look at the transition equations. So this is the difference between those energy levels. We have the Rayleigh scattering, which is just the frequency of the laser that you're hitting it with. The red-shifted transition equation is right here. That's the frequency of the laser minus 4 times the rotational constant times J plus 3/2. And then the anti-Stokes would be 4 times the rotational constant times J minus 1/2. But notice the point here that these rotational lines are separated by this factor of 4b. So if we were to measure this spectrum, we could take the frequency here and the frequency here, and that difference is equal to 4 times the rotational constant. And the rotational constant has that structural information in it, the masses and the bond lengths. This is, I'm trying to write a delta. Yeah, it was kind of a messy one. So that's the difference between those two spectral lines is 4b. Yeah. So here's just a page that shows you the transition equations for absorption. So here's how you, again, get those transition equations. You have the energy equation, which is right here, related to the quantum number J. So J is the quantum number. It's B times J plus 1. And so whenever you're coming up with the transition equation, let's do it for delta J plus 1. So we go from J to J plus 1. Everywhere there's a J in that energy equation, you put J plus 1. So we have J plus 1 times J plus 1 plus 1, or J plus 2, minus J, the energy equation with J. And then you do the algebra. Okay, the J squared terms are going to cancel again. And you end up with this transition equation. So this is the formula for these lines over here. So you could label these with J equals 0, 1, 2, 3, 4, 5. So you could label every one of those peaks, and that's called peak picking. We're going to start doing that in the lab. And if you put in 0 at this, if you put 0 in here, then its energy is 2b. And if you put 1 in there, then it's 2b times 2. So it goes over to 4b, and it's right there. And so you can plot out your spectrum using this transition equation. If we do this for the Raman, Here's the equation, the transition equation for the Raman. It's a 4B spacing. And so these over here, these transitions are spaced by 4 times the rotational constant. So the transition equation tells you what you have in your data. And try to emphasize that. And so we've got 3 minutes. I don't think that's enough for us to even get logged into the Kahoot. But it was, there's a Kahoot on this one. I'll go ahead and click it. You can take it on your own to review the main points from today. Okay. So it's L26. So if you search for 4448, L26, rotational spectroscopy, you'll find this Kahoot. Okay, and you can check your understanding later today. All right, so thanks for your attention. We'll combine these next time and do row vibration. Okay, so it builds pretty quick, and then you'll have a lab on that, so that'll really emphasize row vibration.